assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we have a circular loop here in a uniform magnetic field, and this field is changing over time, so the magnitude is changing. And because of that, we have a change in flux. So if we remember from Faraday's law, it says that if there's a change in flux, we're going to have an induced EMF. And the magnitude of that induced EMF is 0.8 volts. And consequently, the current that gets induced in that loop is 3.2 amps. And what we want to know is if we were to deform this loop here, the circular loop, into a square, what would our new induced EMF be? And what would our new current be? Okay, so first things first, let's just write off some expressions for what the induced EMF should look like for each of these loops. So for the circular one, we know that the induced EMF is going to be the change in flux over the change in time, minus the change in flux over the change in time, where our change in flux is just going to be the final flux minus the initial flux, where in general our flux is just going to be B times A times the cosine of the angle between the surface normal of our loop and the magnetic field. But in this case, since they're parallel to each other, this is always going to be 1 for the whole problem. So really for flux, we're just looking at B times A. And for our circle, the area of a circle is pi r squared. So you can imagine if we define some radius r here, then we could say that the flux is B times pi r squared. And consequently, our change in flux is going to be B final times pi r squared minus B initial times pi r squared. Since our area doesn't change at all, right? Just the magnetic field does. Okay, so let's go down here so we have a little more room. So the change in flux for the circular loop, so we'll say circular. If we factor out a pi r squared, it's going to be pi r squared times B final minus B initial, or just pi r squared times delta B. And if we plug that into our Faraday's law over here, we'll just have that for the circular loop, the induced EMF is minus pi r squared delta B over delta T. Now imagine we did the exact same thing with the square loop here. Notice the only thing that would change is the area of our loop here. So now instead of pi r squared, our area is going to be the area of a square, which is just the length of one side times the length of the other, which is the same, so just L squared. So minus L squared delta B over delta T. Okay. So we know what the induced EMF is for the circular loop, right? We were told that it is 0.8 volts. So if we could relate the EMF from the circular loop to the EMF of our square loop in some simple relation, right? Like if their ratio just came out to a number. If we had one, we could solve for the other. And that's what we're actually going to show we can do. Because, remember, we deformed this loop here from a circle to a square. So what we know about this configuration is that the length of wire we are using is the same the entire time. And the length of wire we used in the circle is just going to be the circumference of our circle, 2 pi r. And we know this is going to be the same that was used in the square, which is just 4 times our side length, right? Or if we solve this for R or L, either way, we'll solve for L, 5 by 4 on both sides. We can see that L is just pi r over 2. So if we substitute out for L in our expression for the EMF in the square here, we'll actually end up in terms of something just in R, which is going to be just like our EMF for the circle. So we could take the ratio and a bunch of things would cancel out. So if we do that, we'll get minus pi r over 2, whole thing squared, times delta b over delta t. Just substituting for L there, which will be minus pi squared r squared delta b divided by 4 delta t. Now notice this looks very similar to our expression for the EMF in the circular loop, right? Has a lot of the same stuff. It's just different by a number constant. So let's look at their ratio now. So E circle to E square is just going to be pi r squared delta B over delta T minus pi squared r squared delta B over delta T for delta T. Okay, so a bunch of stuff cancels, right? Sines, a pi, r squared, delta B, delta T. We just end up with 1 over pi over 4. Or if we flip that over, it's just 4 over pi. So these two EMFs are just related to each other by this constant, 4 over pi. The other way we could have done this is we could have just compared these two equations, this one here and this one here, and seen that they're almost exactly the same, but there is a pi over 4 extra in front of the E sub s. Okay, so now that we know this, we can get the EMF in our square by having the one for the circle. So if I multiply both sides by the EMF for the square, I'll have 4 over pi times the EMF of the square, and then I'll multiply by pi over 4 to end up with the EMF of the square is pi over 4 times the EMF of the circle. So all we have to do is multiply our EMF for the circle, which was 0.8 volts, times pi over 4. And let's see what happens if we do that. We will end up with 0.63 volts. So we have a change in induced EMF because we changed the area of our loop, which means we changed the total flux. Okay, so now let's see what the new current is going to be. Well, if we recall Ohm's law, V equals IR, this relates the voltage drop across a resistor given a certain current. Our voltage is just going to be given by our induced EMF here. So we'll have E sub s equals I sub s times R. So we know E sub s, but we don't have R, so we can't solve for our I yet. But we know that when we do have R, we just divide both sides by R here, we'll be able to get our current. Okay, so how can we find R? Well, if you remember, for the circular loop, we were given the current and the voltage, or the induced EMF. So we can actually solve for our resistance right away. So just using the same equation, so E circular equals I for the circular loop times R, solve that for R. Let's bring it down over here. We'll have R equals E sub C over I sub C. So we're just dividing 0.8 volts by 3.2 amps. And we will have our resistance. which ends up being 0.25 ohms. So now, all we have to do is go plug in our 0.25 ohms here. And we have our EMF, 0.63 volts. So we just divide those two numbers, and we will get that the new current is going to be 2.5 amps. So there you have it. That's how we determined the induced EMF and induced current of a square loop that was deformed from a circular loop when we started off by knowing the original EMF and induced current.